Good afternoon, good evening, and good morning. Greetings from Stanford University, and welcome to the 27th AEC Global Teamwork Final Project Presentation Cyber event. My name is Renate Fruchter, founding director of the PBL Lab, and your host for the day. The PBL Lab is the home of the AEC Global Teamwork course I've been teaching since 1993 with partners worldwide. Our vision is to transform our students' tool set, skill set, and most importantly, mindset, moving from working in discipline silos to work as a single, cohesive, interdisciplinary team and develop fully integrated solutions. Our aim is to prepare the next generation leaders and change agents for the future workplace and challenges that they will encounter. What is unique about this class is that it brings together students, faculty, and industry mentors from 5 disciplines: architecture, structural and mechanical engineering, construction management, and life cycle financial management. Students learn to collaborate in globally distributed teams to virtually design university buildings, addressing local hazards such as earthquakes, hurricanes, flooding, local labor conditions. I have to say, this year has been a great pleasure to mentor and work with highly motivated, creative, and committed students from Stanford and 12 university partners worldwide. Given the unprecedented COVID-19 challenges and shelter in place, we are organizing this annual event in cyberspace rather than having everyone back at Stanford for a final great, engaging celebration. For this purpose, each global student project team prepared a video story of their project evolution. These stories are reviewed and assessed by about 30 industry mentors prior to the May 8th cyber event. But before we dive into very exciting student presentations, I want to extend a big thank you to our industry and faculty mentors, alumni, and owners and sponsors who so generously dedicated their time, attention, and knowledge to our AEC Global students. In collaboration with industry partners, we defined 3 challenges to further foster the students' creativity, focused on sustainability, specifically this year, resilience, integrating project delivery, focused on the question whether to industrialize or not to industrialize, as well as shared risk and reward, and technology innovation, focused on intelligent interoperability between models and disciplines. Winners will be announced at the end of the cyber event, May 8th. So don't forget to visit the PBL Lab Project Gallery website to find out who this year's winners are. Last but not least, a special thanks for the generous support of our technology industry partners that enable us to continue to develop new ways of working and learning by leveraging the latest emerging technologies like VR, virtual reality, AI, artificial intelligence, parametric modeling and optimization, and embed them in the students' new daily work practices that they experience in this global teamwork class. And with that, let's move on to the student presentations.
Hello, good morning, good afternoon, and good evening. We are the Atlantic Team 2020. First, please allow me to introduce our team. We have Maria, our MEP engineer from Copenhagen, Brandon, our structure engineer from Stanford, Ibrahim, myself, one of the construction managers from Madison, Wisconsin, Shuang, the other construction manager from Beijing, and Isabella, our architect, and Louis, the other structural engineer, both from Brisbane. And here, our beloved owners, Dr. Renate Fruchter, Luke, Adam, Elena, and Andre. When the team returned to our home countries and began to work on our concepts, we quickly learned the challenges we would be facing in the project. As the sober global team, we were dealing with 5 different time zones, all while trying to stay connected with each other 24/7. Although a challenge, we were able to identify it as an opportunity as well. Although shared workable hours were limited, they presented us with the opportunity to effectively complete 3 days of work across a 24 hours period. Initially, these time discrepancies made communicating and organizing difficult, but we are quickly adapted using effective technology to allow Atlantic team to progress throughout our conceptual design phase.
This figure shows how every discipline has been actively involved with each other. This is largely due to the technology integration focus that we've had this whole quarter. Louis, one of our structural engineers, introduced the tool as an opportunity to be more united and use parametric design. In subsequent slides, we will discuss what technologies were utilized and how that optimized our team's performance. This figure here gives you an idea of how we progressed throughout the winter and spring quarters. You can see the team developing through the process as we hit different project milestones. What we can also observe from this graph is how our team went through the stages of forming, storming, norming, and performing as we eliminated superfluous meetings, became more efficient as a team. After the winter presentation, we were able to start iterating through multiple designs, so the amount of meetings across the spring quarter became much more uniform than in the winter. Our team's goals stem from who we are as a team and what we want to achieve in the project and what we believe we can achieve for the community through architecture, engineering, and construction. These can be categorized into 3 overarching categories: sustainability, collaboration, and technology, and relate directly to the outcomes we can achieve in this project. We believe in resilience, fostered through community inclusion, compliance with LEED standards, adaptability, and smart design. We aim for a design and construction outcome that is prefabricated and disassemblable. And working towards these goals, we aim to collaborate, be integrated, and connected to both the occupant and the building.
Our project is located at the fringe of the campus of the University of Wisconsin in Madison, located in the Midwest of the United States. Context is the first factor that starts shaping the identity of our building. The Muirwoods as vegetation, the Memorial Library and Union Square as influencing buildings, and the pedestrian circulation in Lake Mildura were selected as main shaping factors. Madison has a continental climate with warm and humid summers and dry and cold winters. There are cold temperatures during approximately 9 months of the year. Comes the need to create a very well-insulated building, but don't forget about the cooling regarding the hot days in summer. Also, the relative humidity on site is slightly high, and it's a factor to consider in the design. For us, it is very important to design a building that meets any occupant's needs. The design should appeal not only to Madison citizens who may be more used to the cold, but to any kind of user. Our site hazards present challenges to the building design and construction, but provide the opportunity for learning and innovating through collaboration. We have taken the site's climate and climate change as the main driver. Our site has extreme cold and snowy days, but gathering the future, this will be turning into warmer and more rainy days. As shown in the picture above, flooding is not as impactful in our site, but still we need to prepare our building for the unexpected. Our aim is to design a tight building envelope in a short time due to the weather conditions and be able to manage and mitigate the water. The building orientation was selected in order to take the maximum advantage of the local sun, climate, and geography. Our site occupies the intersection between the campus life and the spectacular geographical beauty of Wisconsin and Lake Mildura. While presenting opportunities for its views to the lake and Muir Hill, our site is constrained by its lakefront location, single site entry, as well as a single tight and limited access. An important aspect of the building orientation is to determine how the stand positioning affects the building design. Our building orientation and architectural design intends to make the most of the outdoor and interior layout while advancing in our key goals. The analysis has been possible thanks to a parametric sound path study through Grasshopper software.
Throughout the program, we developed two driving concepts, both of which underwent much iteration and evolution. The first was finding a forum, and the second was weaving. Both concepts evolved from a singularity to an integrated driving processual idea that generated a spatial quality for the building. For our concept selection, we wanted to emphasize that the best option should not be chosen simply based on a number. We wanted to evaluate the intangible and tangible aspects of both building concepts. The tangible criteria of our decision matrix integrated our team goals, and project challenges. They bring together everything that we're looking for. The intangible criteria are not as readily quantifiable, but are equally as important. After completing the decision matrix, we actually had a tie between forum and weaving. Ultimately, we decided as a team to add one more criteria, challenge. Which concept would challenge us to further encapsulate our team goals? That is to say, which would push us to integrate, to learn, collaborate, and be innovative in our solution. Because of this, we decided to bring forward the weaving concept into the spring quarter. Weaving is both our team's process and the conceptual driver. It's a singular concept and yet implies the process of combining and integrating. We draw on the local historical practice of weaving, which extends from the basket weaving practice of traditional owners to textile production as a part of the arts and crafts movement. Weaving as a process unifies the threads of sustainability, prefabrication, and discipline knowledge into a building for the future.
As a team, we decided the weaving concept was best conveyed through the facade. Our team's goals and values were reflected in the facade and its iterations, and all disciplines worked together to devise a solution which met these goals and tackled the three challenges. We aimed to produce a facade which was easily assembled and disassembled, contributes to the building structurally, and enhances the building's energy performance. Throughout the presentation, we'll be using icons to represent the different software and technology which was used. These also include several plugins for Grasshopper, which assisted in various design and analysis tasks, including Honeybee and Ladybug for solar and daylight, ArcSim for energy, Karamba for structural analysis, and Speckle, an open source cloud-based platform for interoperability. These icons will be displayed in the upper right corner of your screen on slides to indicate which software was used. Grasshopper, a parametric design tool, was used to iterate the facade geometry. This allowed us as a team to rapidly explore the implications, changes of key parameters on the building, and therefore make smarter and more informed decisions at earlier stages of the design process. The chosen control parameters allowed us to generate facade solutions which integrated all of our goals. Revit models were produced using Grasshopper, allowing detailed models to be produced at early stages of the design. This allowed us to present designs to our owners frequently and bring them along the design journey with us.
The building product synthesizes the challenges of the previous iterations into an offering that interacts with its spectacular geography and creates a space for learning, for teaching, and making for a new generation of engineering professionals. The Lakeside Plaza provides a gathering space and extends into the ground floor lobby, into which the stair, the connective thread of the building, descends. The stair forms the heartbeat of the building, connecting people and physical space. Visual transparency through the building aims to encourage an atmosphere of inclusivity, relaxedness, and openness within the building. The building's architectural expression is evocative of weaving through pattern, texture, and the interplay of light and shadow. It combines innovation with sympathy to its context by mirroring the setback distances of its neighbours and the civic contribution to public lakeside space. It also extends the cutting-edge contemporary architectural language that's evolving within the campus. The ground floor includes learning spaces such as instructional laboratories, an auditorium, and building amenities, which are centered around a generous public-facing lobby. The mechanical room is placed in the ground floor, and a vertical shaft with the building systems is extended through all floors. By centering the mechanical room within the building, the access bisects the building, thereby allowing adequate ventilation throughout while minimizing heating and cooling on one side.
This slide shows how the MEP and structural engineers work together to integrate the design. For a structural system, we chose to use timber materials. Actually, the first use of glulam in the United States was in Madison in 1934. In our grid system, we use one column size and only two different beam sizes. Our core walls are represented by the green rectangles are constructed of CLT panels. Our grid system is a pattern that is concentric to the facade because our floor panels actually sit within the facade system. Our facade will provide uniform support to the CLT slabs along the building's perimeter. The beams in our grid were designed to not frame into the facade due to structural and constructability difficulties. Furthermore, disassembly of the facade would compromise the integrity of the building if the beams were framing into it.
A main goal and challenge for the architect and the mechanical engineer was to create an interior design that responded to daylight and energy efficiency. For this, a daylight and energy analysis have been carried out for each floor with Grasshopper. The south windows get good sunlight and allow for extra heating in the cooler months, lowering the heating demand. And the east and the west windows are offset from the sunset and sunrise, which lessens the design cooling load.
Within a workspace on the ground floor, we see how the pattern created through opacity and transparency at the facade translates to a dynamic, warm learning space, fostering a thriving community founded in student engagement and comfort. At the mezzanine level, learning spaces are centered around the connective stair, which connects levels physically and visually. The auditorium on the eastern side of the building is in close proximity to seminar rooms and spaces for learning and gathering.
The sun provides superior natural light for the occupied rooms located in the back, in the first and the second floor. For the ground and mezzanine floors, the spaces that don't require daylight have been allocated in the back, as we have a hill that blocks the daylight.
The auditorium offers a warm and flexible learning and presentation space with express structure and internal registration of the building form. The retractable seating design allows the space to be used in a multitude of ways and adapts to its owners and its occupants, ensuring resilience as time and needs evolve. An integrated mechanized track shading system provides complete flexibility, with windows able to be covered by flush timber panels for presentation mode or retracted to provide natural lighting and views to the lake. At the first floor, faculty offices are gathered around a central open workspace, which allows staff and their students to meet and collaborate informally, the planning fostering connection between building users through functional, delightful spaces.
You can see that our structure begins to extend on the south side of the building. We use deep beams on the first floor to remove columns near the entrance and open up floor space. You can also see here how the MEP aligns with the grid, weaving within the structure.
The faculty lounge, classrooms, and offices have been allocated in the south, north, and east facade, providing the natural light entry. For the offices and other internal workspaces, the furnishings parallel to the windows have a maximum height of 42 inches to allow the daylight entry.
The faculty lounge, located on the second floor, offers spectacular views to the lake for all staff, rather than visual amenity being restricted to the few. The shape and size of the glazing not only capitalizes on views, but enhances natural lighting and user comfort. A place for gathering, interaction, and reprieve, with integration of contemporary artwork, it makes this place a celebration for its staff. The weaving concept's extension into planning is exemplified as opportunities for spontaneous interaction and collaboration are maximized, as work pods or nooks within the breakout space weave learning spaces into the public area.
Because of our exposed timber system, the mechanical systems were placed beneath the structure to allow for easy integration. With the ventilation system selected, we were able to reduce the equivalent floor-to-floor height, thus improving the user comfort.
For the top floors, shading should be used in the south facade to avoid overheating and user discomfort, so it seemed crucial to use the same software to do a glare and shading study. This one has allowed to find a shading design that optimizes daylight and ensures glare comfort. Also, by studying the daylight coming to space, the glazing use of the building has been optimized, and this is reflected in the facade cost, energy performance, and daylight conditions.
The second building entrance at the south carves an activated concourse through the building interior, and it provides views through to the lake at the north upon entering the building from the campus side. The folded exterior expression is continued inside to create an inviting and dramatic procession into the building. The use of timber within the interior design fosters a connection between the material experience of the building and its construction elements, framed against glimpses of Lake Mendota. Floor and joinery finishes were selected to create a neutral background to the vibrancy of campus life, and light tones reflect light to create comfortable, enjoyable spacings for reading, work, and collaboration. Learning spaces also embody the dynamism of the learning experience with warm, neutral materials contrasted with vibrant colour. Building structure and MEP solutions are woven into the daily experience of the student and facilitate an environment where the building itself teaches the students about construction and about design.
Smart control units and sensors aid in the monitoring of the building. Sensors can be found in the lights and HVAC systems, improving the building energy performance. We aim to create a building so smart and intuitive that knows exactly how much energy is consumed and adapts itself based on the weather, season, and work patterns.
In a meeting room, the weaving concept is extended into the architectural details. A frit pattern applied to the glazing not only provides privacy, but references the building's contextual history through the abstraction of the weaving pattern. Cutting through the building shows the visual transparency between levels and their spatial connectivity via the stair. We can also see it between forest and lake and the maximization of these two visual resources. The building expresses the notion of weaving through light, shadow, and texture, integrating user needs with disciplined solutions to create a dynamic, iconic building for a new generation of engineers, educators, and administrators of the University of Wisconsin-Madison.
When we began to conceptualize our building, we started by thinking about how our solution could be a reflection of our team's goals and values. All of the constraints listed on the screen contributed to the realization that a prefabricated engineered timber building was the most suitable building solution. This would help reduce on-site activities and construction time, minimize the building's carbon footprint, and aid easy assembly and disassembly. The woven pattern was achieved using 3 different module types. 2 different sized timber modules give the facade its noticeable texture. At the same time, the facade was parameterized to make sure it was not too visually complex, and the number of assemblies of modules was at a minimum. Assemblies also consist of glazing panels, which provide the building with adequate daylight. The facade consists of solid timber modules in vertical channels, which provide support to the floors and contribute to the woven pattern. Timber modules consist of 3 4-inch by 4-inch timber studs wedged between 2 3/4-inch plywood sheets. Structural timber modules are 3 feet long and non-structural modules are 8 feet long. All modules are 2.8 feet high, which allows for 5 modules to be stacked within the floor-to-floor slab height.
The facade will be constructed floor by floor, with modules built into 5 different assembly types. Each floor is 5 modules high, and we need the top and bottom modules to be timber to allow for ease of construction. This meant that the glazing was placed in the middle of the assemblies, affecting the aesthetics of the weaving pattern. But we were able to minimize the number of assembly types by iterating with parametric design. The Urban Land Institute defines resilience as the ability to prepare and plan for, absorb, recover from, and more successfully adapt to adverse events. The vision for Team Atlantic's design was to allow the building owners to prepare for and adapt to future adverse events. We believe that this can be done by creating a building that adapts as quickly as its occupants.
If you've ever put together a piece of IKEA furniture, this image may feel familiar to you. In the same way, the Atlantic building is explicitly designed as a kit of parts, which can be disassembled and reassembled. Facade panels, CLT floor panels, beams, and connections can all be reassembled to adapt to the changing requirements of its users and its context. The only way to ensure genuine resilience in a world of constant change is to be truly adaptable. Here we can see one of the many potentials for what the building could become should it require a second life. While panel sizes are designed for the uniformity and breadth of building application, the Atlantic building would be perfectly suited to the creation of social housing. This potential use contributes to the resilience not only of this single building, but of the community as a whole.
Initially, Brandon and I investigated the use of HFT panels as an alternative to CLT floors and walls within the building. HFT is a panelised system using low quality and cheap plywood and veneers reinforced by GFRP. It has equivalent strength characteristics to CLT, but with 66% less mass. After the winter quarter, we decided to use HFT. However, we since realised this would not be feasible to integrate with our facade. Vertical loads are carried by beams and columns into reinforced concrete pad footings. A shallow foundation system was required due to the high water table at the site, and so 3 feet deep footings founded at 3 feet below ground level were chosen. The base of the facade will connect into an RC strip footing, which protrudes 3 feet above ground. This raises the building above the predicted flood height. The southern face of the building is supported by a reinforced concrete strip footing on the hill. The region beneath the step onto the hill will be backfilled with soil, which will be resisted by a steel soldier pile retaining wall. The perimeter columns also contribute to the lateral resistance. A workflow was devised which integrated the structural design and modelling into a single process. The grids were set up manually alongside Isabella within the architecture model, coordinating column placements with the interiors. These grids would be sent from Revit using Speckle and brought into Grasshopper. The Grasshopper script would generate the analysis model from the grids using Karamba, and Rhino Insight was used to create the Revit model using the required member sizes from the analysis. Keeping the analysis within Grasshopper, we were able to allow the design to be completed alongside the Revit model. Member sizes could be given to other disciplines quickly, especially when space proving with the architect. We could then reduce time spent doing clash detections and re-exporting models. The outputs of this workflow were also thoroughly checked by hand.
Our connection details were designed to allow for ease of initial construction and future disassembly. These timber connections are all hidden to the public eye, but are essential for the construction speed and efficiency. The connection hardware is structural and connects the structural and non-structural modules together. These modules have solid timber that allow for sturdy connection hardware and recessed connections. These connections also allow for easy design for disassembly and load transfer between vertically stacked modules. What is critical for these connections will be the tolerances, but this can be achieved with industrialized construction. Another important feature of the structural facade is the detail connecting to the slab. The connection will account for environmental factors by extending insulation below grade, incorporating a waterproof membrane and sill plate beneath the module, and raising the concrete strip footing above grade to also allow or protect against flooding events. The connection between the timber modules and CLT slab is an adaptation of a standard CLT connection using dowels. The advantage of the dowel connection is the ability to conceal the connection. In addition, the dowel will be inserted into the center stud to not intersect with other hardware. As we have mentioned, the gravity loads from the slab will be transferred between the internal grid and the facade modules. The narrower structural modules are the stiffer elements and will carry the loads. The non-structural modules will only carry the self-weight themselves. The lateral loading from wind will be transferred into the dowel connections that are approximately 8.5 feet on center. One of our primary challenges with the facade was to deal with the effects of weather. The timber is on the inside of the complete built-up module. From there, we devised a system of moisture protection, insulation, and flashing that is enclosed within the timber cladding. The insulation and flashing overlaps from one module to the next to ensure protection from the elements in continuous timber cladding. Another challenge was designing the glazing modules. We first conceptualized the module connection as a team and then worked with Alpen Thermalbuck to design feasible module connections. The design allows for the timber and glazing modules to separate in disassembly. In addition, we designed the glazing connection on top of the module to allow for displacement, thus effectively acting as a pin connection.
To achieve a high level of energy efficiency, it is important to pay attention to the building envelope assembly. The window plays a very important role in this stage. Our window solution consists of a double pane that integrates a thin glass into the insulated glass unit, and it is double insulating compared to conventional windows. The insulation of the facade has been also carefully considered, and it is important to create a tight envelope that minimizes energy consumption while being able to manage the heat gains in the hot days. For the HVAC, ventilation has been decoupled from the heating and the cooling system. This allows downsizing the equipment, reduce costs, energy, and space needs. The indoor air quality is achieved through the fresh air, while thermal comfort is provided by the heating and the cooling system. The ventilation is supplied by a dedicated outdoor air unit, which provides 100% outdoor air. Considering our site challenges, the system performance is further improved by using energy recovery, a dehumidifier, and filters, and this comes with improved energy efficiency and user productivity. The DOAS is capable of monitoring and directly controlling the outdoor airflow and ensures that it doesn't fall below the minimum required. Every space of the building has CO2 sensors to maintain CO2 levels within the respective spaces. With the solution, the indoor environmental quality is ensured. So the first step to select the heating and cooling system is to gather the overall context on site. It is important to see what is available and what can benefit the solutions. Our site is surrounded by a lake, and a cogeneration facility supplies the energy source to other buildings from the campus. Medicine is well known for biofuel production, and around campus many biofuel farms can be found. But does it make sense to use this waste to provide heating for the building? Another solution to manage simultaneous heating and cooling loads was the use of a heat pump, but would it be more economical or efficient? After detailed research, the West Campus Central Plant was chosen to provide the energy source. With this solution, another instance of native-to-place design is shown. It is a very economical and energy-efficient solution and follows the owner's requirements and project goals, and also the facility plans to be more sustainable in the future, reducing the carbon emissions. The schematic intends to show the energy source management of the building. The coaching facility provides steam and chill water for the hydronic systems, and circulation pumps driving the district water are used to ensure the hot water is circulating at all times. For the secondary system, underfloor heating cooling is integrated in all floors of the building. Additionally, radiators have been placed in specific spots according to the loads and the possibility of interior design. The chosen strategy intends to satisfy not only the interior of the building, but the building body itself. According to our goals, to make an intelligent building connect to the user, a zoning system is integrated in every floor. This one learns from the user behavior, adjusting the settings in the long-term view to provide the best comfort. A first step was to calculate the heating and cooling loads for each space. The ArcSim plugin for Grasshopper was used to conduct the energy simulations. The floor plans were sent by a speckle from the architectural Revit model, and the script extracted the zones and ran the simulation. To determine the thermal zones, thanks to a collaborative work with the architect, the areas have been grouped together with similar positioning and thermal conditions. The location of the spaces is based on the combination of the daylight and the energy results. The auditorium has been treated as a separate zone, as having high variability in occupancy. Here, the outdoor air is directly ducted to fan coil units. With this choice, the space receives appropriate ventilation levels, as well as being worked up in a faster way than using hydronic floors. Demand control ventilation also seemed a good choice, and the baseline system has led to decent savings due to the reduced required outdoor air. Solar energy was considered to reduce the use of energy from the grid and improve our site carbon footprint. To see the building potential, a radiation analysis through Grasshopper was done, and given the results, it seemed as a right decision to integrate PV for such a university building. The weaving harnesses the sun with 224 photovoltaic panels distributed across the building's roof. These are fixed at an angle of 10 degrees, allowing the maximum energy production. Additionally, to manage the water on site coming from the precipitation, it seems crucial to design a drainage system. So water is collected through a drain channel located in the roof, and this one is redirected through soundproof insulated pipes. Over the course of the year, PV accounts for almost 50% of the electricity demand. This PV system is always connected to the grid and follows the Wisconsin's approach of net method systems. The directly generated kilowatt hours are directly offset by the consumed. To manage and mitigate the water, the urban planning has been carefully studied. Native plans minimize watering requirements and maximize rainwater absorption. In addition to contribute to the team's sustainability and LEED goal, the building water consumption has been carefully assessed, and by implementing sustainable toilet fixtures, water has been reduced up to 40%. Lastly, the drainage from the roof is collected and will be reused for toilet flushing. A cistern is placed in the west side of the building, and it is sized to meet 25% of maximal rainwater collected in a year, and this ensures the water is running even if there's a 3-month period with very little rainfall. Finally, for the sustainable target value, the team has been on track during both winter and spring semester. By choosing a mass timber building, we have further improved the sustainability of our project, and also by implementing energy efficient solutions, we have been successful in achieving a good environmental performance.
Technology has allowed us to deliver an integrated building solution for our owners. By leveraging it appropriately, it has allowed us to create a highly interoperable and streamlined workflow. Part of this also meant assessing the suitability of processes within the workflow and whether or not they will add any value to the project for our owners or make our lives easier. From a technology perspective, intelligence means finding the right combination of processes which will maximize value. Not all processes require technology. These criteria were used for determining which processes should contribute to our integrated workflow. Using this criteria, we were able to create a workflow which considers intelligence from a variety of angles. Ultimately, meeting this criteria would result in the most efficient and value-driven workflow. Our solution to the challenge was broken down into 3 stages. The design and modeling stage, tackling discipline workflow integration and modeling production. The manufacturing stage, where technology was used to assess the most suitable approach to construction of our building. And finally, the data visualization and design record stage, where key design data was aggregated and published. In the design and modeling stage, Grasshopper was selected as the primary tool as it allowed us to explore the impacts of different design decisions all within a single workflow. We have leveraged Speckle to link Grasshopper and other platforms to each other and use this real-time data transfer to drive our models and our processes. Given our facade model was produced using Grasshopper, other processes were easily integrated within the facade solution. The final output of this stage was an integrated Revit model driven from real analysis results and data. This model then provides the link into the manufacturing construction stage, where technology was used to determine whether or not we should industrialize.
A progressive cost estimation approach has been carried out throughout the project. Using DynamoScript, it has been possible to have an automated quantity extraction. With it, an Excel sheet was shared with subcontractors and suppliers to have fast quotes and cost input. The database was then fed into WNS detailed estimation to investigate the cost breakdown. And finally, the TVD sheet was used to value-driven improvements involving all team disciplines. The following cost tracking timeline shows 4 major design changes that reflect the team collaboration and innovative ideas. First, heat pumps were replaced by getting chilled water from UW-Madison cogeneration facility. The latter has less running cost, better efficiency, and maintenance services. Second, the double skin facade was replaced by a single skin facade through optimizing glazing and wood panels using parametric design. This resulted in a better energy performance, reliable design, and higher value for money. Last, interior wood studs were replaced by metal studs because of the high reusability of the latter. Also, it takes less time to install as no pins are used between each stud. The bar chart shows a comparison of our cost against the team targets set early in the process. In services, direct quotes from suppliers and contractors allowed for reduced and accurate cost estimation. As for interiors, our cost is slightly higher than the target due to using monomelene flooring. However, it is considered the only CO2 neutral resilient flooring and the best choice for every sustainable interior. Finally, thanks for parametric design that helped significantly in optimizing glazing density and geometry. The following shows the equipment that will be used for our project. Accessibility and sustainability factors have been considered when selecting equipment. When investigating two types of cranes, we investigated two types of cranes, fast erecting tower crane and mobile crane. Mobile cranes have better lifting capacity and can change position easily. However, given our tight site access, they will worsen the traffic congestion if used frequently. On the other hand, fast erecting tower cranes are better suited for constrained areas with high material handling efficiency. We decided to utilize a mobile crane for only one pickup to lift the dedicated outside air system. Also, a fast erecting tower crane will be used to lift the structural and the architectural elements due to its efficiency. The following set of criteria and factors were considered when tackling the DPR challenge. These were divided into risk and rewards. Rewards include reduced labor cost, less waste, less direct cost, quality improvements, and just-in-time delivery. Among risks are increased front-end planning, tolerances inaccuracies, the right time to place the order, optimized deliveries, multi-disciplinary coordination, and fragmented supply chain. Since the woven facade is the overarching concept in our project, the Atlantic team developed a selection framework to choose the best option to construct the facade, given the project conditions and the site context. Therefore, the following decision tree starts with investigating whether prefabrication is feasible or not, and if yes, shall we go fully or partially? Under each option, we can produce large or small panels. Large panels are characterized by higher construction speed, less connection cost. However, they will impact the crane selection and require large store space. On the other hand, smaller panels allow for architectural freedom. However, they will impact transportation and installation efficiency. Thanks for Grasshopper, we were managed to accurately quantify glazing and plywood panels per each assembly. Cost has been calculated using direct quotes. Cost has been calculated using direct quotes from suppliers. Also, time has been calculated multiplying labor productivity rates of each option by the quantities identified. For prefabrication alternatives, an improvement factor has been applied to account for the higher efficiency. This shows that prefabrication of large panels option has the least time and cost. Choosing by advantage was used to account for logistical and coordination success factor that would impact the decision process. In general, off-site prefabrication yielded better results. However, there are some risks that shall be mitigated. In order to enhance Atlantic team cross-disciplinary teamwork and business processes, the following framework was developed to provide real-time integration starting from design and engineering, then manufacturing and construction visualization. This enhanced the overall agility of the team to iterate, measure, and implement design changes and quantify their impacts. The framework consists of the three workflows as follows. The first workflow allows for investigating the design impacts on industrialization in real time. Using Manufacton software, Atlantic team was able to integrate all information needed for prefabrication in one location for more transparent and collaborative work. Also, we were able to view the status of each assembly in our facade in real time. Finally, we could measure how certain design change would impact our bill of materials and prefab orders. Fragmentation in the supply chain was one of the risks identified earlier. Using Manufacton, Atlantic team was able to track the status of the prefab orders utilizing supply chain viewer. Each status corresponds to a specific color code. Atlantic team also quantified total productivity gains when shifting work to off-site. According to the current analytics, productivity has been enhanced by 30%. In general, a productivity range between 0.6 to 0.8 is desired. Automated generation of bill of materials for prefab orders using Manufacton helped the Atlantic team to first quickly identify sub-assemblies quantities and secondly, to automate the cost estimation process as well. We managed also to track productivity gains for each step in the production line. For example, using Manufacton, we identified the current coordination time lies in the risk area and that more coordination is needed to achieve higher productivity gains. The second workflow is developed to simulate and optimize construction operations after prefabricating the panels. Any logic simulation was used to compare different transportation and installing scenarios. Alice then was used to optimize construction schedules and sequencing. Finally, Fuser was utilized to simulate week workflow, site logistics, and operations. Atlantic team simulated the process of shipping and installing panels on site for two scenarios. The first scenario is fully prefabricating the panels, and the second is to prefix connections on site. Using AnyLogic, two KPIs were investigated. The first KPI is the total time needed for shipping and installing the panels. The second KPI is the pre-assembly area required. Also, we modeled risks associated with both scenarios, such as tolerance accuracies and coordination delays. The video shows the model that has been developed to quantify the two KPIs in both scenarios. In short, total prefab yielded better results in our case, even with the delays embedded within this option. The following step was to investigate schedule alternatives and zoning options. Using Alice, we first investigated whether dividing our project in 3 zones would impact cost and time. The comparison shows that no zoning strategy yielded better results. Secondly, we investigated the key drivers for our selected zoning strategy. As such, we ran a second comparison where we double facade crews and let them work more shifts. Surprisingly, this option yielded better cost and time results. Applying the sense rule, we can notice that schedules with duration less than 150 days will have significant time-space constraints due to the crew congestion. The logical following step was to investigate how we will plan out our site logistics. First, we imported Alice's schedule Excel sheet into Fuser to build up activities and tasks. Then, we investigated 2 strategies, barge and land. In order to make use of the water body and as an asset, we opted to use the barge to store materials and provide massive pre-assembly areas if needed. The Atlantic team investigated also the environmental impact stated by Chapter 30 in the state of Wisconsin. However, pedestrian safety, cost, and material loading were significant drawbacks in this strategy. As such, we pivoted to the land strategy and tried to mitigate the disadvantages associated with it. Peak workflow day has been identified using Alice, where we have complex on-site operations and several crews working within proximity in addition to the equipment movement. The following video shows space-time conflict between 2 forklifts. We can notice the crane is lifting columns and CLT panels while a forklift is heading to pick up the facade panels from the truck outside. Simultaneously, another forklift will appear now and it picks up interior walls will be in the path of the first forklift. In order to overcome this problem, we investigated shifting the trailers to flow over the lake. This will help providing more free spaces for equipment to move and also increase workers' morale and motivations. However, we had to make sure that this solution is feasible first. According to Alice, our project will be mostly executed during the summertime. Therefore, there is no weather issue. Also, one interesting insight that we managed to figure out through Alice, through Fuser, was how we're going to actually install interior walls if our facade is structural. We investigated if we can ship the interior walls early in the project. However, simulating this in Fuser showed that there will be congestion and will limit space for other trades. As such, we decided to leave 2 vertical openings at our facade to allow for interior walls entry after consulting with the structural engineers. This will actually help reduce congestions and heavy equipment movement on site. Also, it will help with just-in-time delivery and reduce quality risks. The video actually shows the sequence and the time when we have the 2 vertical columns enclosed. The third and the last workflow is to investigate how constructability, safety, and logistic issues can be mitigated early in the design process. Clash detection analysis has been run Then VR softwares like Prospect were used to visualize the issues. After changes are discussed on the team level, they are augmented with the integrated Revit model. Following integrated project delivery principles, Atlantic team developed an Excel tool to assess risk and rewards associated with design decisions and prefab options. The process starts with a detailed description of the change. Disciplines affected by the change then meet to discuss the cross-disciplinary impact. Summary is then reported during the team weekly meeting to propose alternative ideas, quantify the impact, and finally approve or reject. To promote transparency and trust among team members, the tool has been integrated in the IT challenge solution. Strategically, our framework builds a highly collaborative, agile, and innovative team. The process is concurrent across all disciplines and openly shared. Risk is managed collectively and equally. Communication is virtual and relies heavily on only one single source of truth. Finally, we build solid ties of trust and cooperation not only among us, but also with our clients. The three previous workflows have been integrated with the rest of the IT framework to link engineering and design upstream with manufacturing and construction downstreams.
This end-to-end integrated workflow has been crucial for us to produce detailed facade iterations developed off of analysis and real data. Given the majority of this workflow has been completed using Grasshopper and Speckle, key design information which contributes to the design iterations can be extracted from the streams or the scripts into a single location. This information was stored in Excel or Grasshopper and then sent using a single Speckle stream to a central Grasshopper script, which aggregates all of the information. From here, the Shapediver plugin was used to generate a web application which hosts this information, as long as all of our design iterations. This allowed us to bring our owners along the design journey with us, as well as track a history of why key design decisions were made. The interactive browser allows the user to visualize all design iterations and the associated data contributing to the design changes.
In summary, our answer to resilience has been multifaceted and based not only on resilience for a single building, but resilience for the community as needs and context change. At the building level, it's included water-sensitive design, reuse and reduction, adaptable and flexible spaces such as the auditorium, and a building solution intricately and expressly designed for disassembly and reassembly. Returning back to our project goals, our goals stem from who we are as a team, what we want to achieve in the project, and what we believe that we can achieve for the community through architecture, engineering, and construction. They were distributed into three main categories: sustainability, collaboration, and technology, and were integral in guiding our team's process. We were able to achieve our goals through our unique solutions to each of the challenges. Through focusing on discipline and platform interoperability, resiliency, industrialized construction, and risk and reward thinking, we inherently grew stronger as a team. Our team learned a lot and had a lot to say over the past several months.
This project was a massive and challenging endeavor. So much international and industry collaboration was essential to the accumulation of knowledge and experience on this project. We appreciate every phone call and every email we've exchanged with all of you volunteer mentors. Most importantly, we recognize and appreciate the unyielding time and effort Dr. Renate Fruchter has put into this coursework and team experience for us all. Finally, the people of the Atlantic team are proud to present the final product of our hardworking and rewarding processes. Plus, we invite you all to join us and experience the building application for yourself and get a better insight into how our facade became what it is today. Thank you on behalf of the Atlantic team.
Well done. Thank you very much, Atlantic team. Inspiring exploration and joint decision making. Thank you, and we look forward to the questions from the mentors and the fruitful dialogue May 8, 2020.